If you like my channel, chances are you've probably heard of Barnard Star in the last few weeks, thanks to the rather surprising planet that has just been announced to be, very likely, orbiting it. I wouldn't hold it against you, though, if, prior to the announcement, you had not. As stars go, Barnard's has not drawn many down its off-ramp from the speedway of life. Bar a brief mention in The Hitchhiker's Guide to the Galaxy, it hasn't even had much impact on science fiction. And this is odd, because Barnard's is a unique star, with a fascinating history, and if you're prepared to take the long road, I'd like to tell it to you. Here's something you don't hear on YouTube very often. Turn off your screen. Not now, obviously. Wait until you have a clear night sky. Ideally, you should try this at new moon, when the skies are darkest. Then, travel however you can, as far away as possible from any urban center. Your destination should be somewhere high and dry. The Colorado Plateau is ideal. Or, if, like me, you are cursed to live in the astronomically dismal UK, try the Brecon Beacons in Wales or Sark in the Channel Islands, both official dark sky zones. Don't bother with telescopes or other such flummery. We didn't need them for 300,000 years, and you won't either. Once you've settled in, perhaps with a cup of hot tea and a shiver, turn off all the lights you brought with you, and wait for your eyes to adjust. Now, look up. What do you see? For the average person, the spray of stars across the field of the night sky can seem overwhelming, uncountable even. But I'm afraid that impression is false. If, like the vast majority of people, you live in the northern hemisphere, over the course of the year, and given clear nights, you will be able to see about 5,000 stars. Southerners will see about 4,000. The reason one cannot be more precise is that no one sees the sky in exactly the same way. Some will see more stars, and some fewer, but none will see much beyond that. Given this, it's not surprising that so many of our best-known stars have individual names. When Ptolemy, or Hipparchus, the debate is eternal, composed his catalogue of 1,028 stars in the 2nd century AD, he accompanied the positional information with quick descriptors, such as the left foot of the centaur or the right elbow of Hercules. When Arabic scholars, supplementing their own observations, translated his catalogue in the 8th and 9th centuries AD, they preserved these descriptors in their own language, often with little regard for ancient Greek mythology. The head of the Gorgon became Ra'as al-Ghul, the head of the ghoul, or demon. The right shoulder of Orion became Ibt al-Jawza, or the armpit of the central one. The tail of the swan became Dahnab ut Dajaja, or the tail of the hen. When Latin translations of the Arabic translations of Ptolemy reached Europe, these phrases were garbled and their meaning was lost. They went from simple descriptors to actual names. Ra'as al-Ghul became Algol, Ibd al-Jawza became Beetlejuice, and Dahnab ud Dajaja became Deneb. In 2017, the International Astronomical Union, or IAU, the body responsible for standardizing stellar nomenclature, officially recognized the proper names of about 330 stars, the vast majority of which are of Arabic origin, as evidenced by the ubiquitous presence of the article Al, Algol, Altair, Alcor, Aldebaran, Alnitak, Alphard. The same holds true, incidentally, for alcohol, alkali, alchemy, and algebra. It was a fertile time, but that is for another video. The numbers of the fixed stars would remain, well, fixed, for 1,300 years. Even Tycho Brahe's blood-sweatingly precise survey only uncovered a total of 1,004 stars. But then came the telescope. In 1725, John Flamsteed's posthumously published telescopic catalogue charted 3,000 stars. Between 1859 and 1903, aided by the advent of photography, the Bonn Observatory's Durchmusterung catalogued over 900,000 stars. In the 1980s, a catalogue intended to guide the Hubble Space Telescope plotted the positions of 15 million stars. And this year, Gaia, a spacecraft specifically designed to accurately determine the locations of stars, released a total of 1.7 billion. But even that is just a tiny fraction of the number of stars we know exist in our galaxy, to say nothing of those we've seen in other galaxies. Given this, it is unsurprising that granting a star the honor of a name has fallen from fashion in recent years. Of the 330 or so names approved by the IAU, only about 30 post-date the invention of the telescope. For a star to earn a name today, it must distinguish itself even from among the billion our tools have pinpointed. Proxima Centauri earned its name because it is the closest star to our own Sun. The 17th century astronomer Johannes Hevelius christened the red giant star Omicron Ceti Mira, or wonderful, because it was the first variable star to be described. Astronomers are in the habit of giving stars names. Fans of astronomical YouTube can certainly recall Tabby's star, which probably isn't orbited by an alien megastructure. Or perhaps Przybylski's star, which probably isn't an alien nuclear waste dump. But these names are unofficial, basically nicknames to skirt the awkwardness of catalog numbers. To date, only 6 stars have been formally named for people beyond myth. 2, Cervantes and Copernicus, were named in 2014 as part of an IAU publicity stunt. 2, Suwalkin and Rotanev, were slipped into the 1814 Palermo catalog by Giuseppe Piazzi's assistant in a moment of personal vanity. The words are anagrams of his Latinized name. 1, Cor Caroli, or Charles's Heart, was named in honor of the British King Charles II by his personal physician. Only one star in history has been officially named to honor a man's achievement in connection to it, and that is Barnard Star. Edward Emerson Barnard did not discover Barnard Star. If he had, it would likely not bear his name. It had actually been snapped by the Harvard Observatory about 30 years before he glimpsed it in 1916. Barnard's achievement was far more significant. He found what made it unique. Edward Barnard's remarkable life reads like a literary fusion of David Copperfield and Huckleberry Finn. He was born in 1857 near Nashville, Tennessee, though he never learned precisely where. He had seen a photograph of a red brick hovel in a fetid swamp somewhere near the outskirts of town and assumed it was his birthplace, but he doubted it still stood. His father was already dead by the time he was born, and at the age of 4, he found himself swept up in the bloodiest conflict in American history. He often spent his nights outdoors, lying on a wagon bed, looking at the bright star Vega as it hovered over the horizon, listening to the boom of Union artillery as it edged closer to his town. Through the hell of Reconstruction, he fled cholera outbreaks and dove into the Mississippi to scavenge cracker boxes from sunken riverboats. When he was 12, his mother succumbed to what was likely Alzheimer's disease, leaving him effectively orphaned, though with the added responsibility of an invalided mother to support. Thankfully, a childhood contact of his mother's happened to own a photography studio in town, and required a hand to guide his gigantic solar camera, a cumbersome beast that focused sunlight on giant panes of silver nitrate that allowed photos to be enlarged by up to 10 times. From the age of 9 until the age of 25, the operation of this camera was Barnard's career, and his family's sole means of subsistence. While operating the camera, Barnard made his first astronomical discovery. The striking of noon by the local church bells did not always precisely coincide with the sun's highest point in the sky. This was, he later learned, because Earth, following Newtonian mechanics, does not travel at a consistent speed around the sun. When closer to the sun, it travels more quickly. When farther away, it travels more slowly. Clocks were set not to actual noon, but to a fixed time tied to an averaged speed for the Earth. He hadn't even considered becoming an astronomer, however, until, at age 18, a chance encounter with a ne'er-do-well acquaintance from his destitute childhood left him with a tattered book as collateral for a never-repaid $2 loan. The book contained maps of constellations, guides to telescope use and maintenance, and essentially all required knowledge for an aspiring stargazer. Barnard was hooked. He asked a colleague at work, a brilliant experimental mechanic named James Braid, to build him a telescope, and, after finding a Confederate soldier's spyglass lying in the street, Braid did so. It was a hefty favor, but, as Braid noted, quote, "The telescope gave Barnard more pleasure than anything else in his life," unquote. Which, to be fair, is not hard to believe. Soon, Braidscope was not enough, and Barnard went literally for broke, putting money down on a $380 telescope, more than half a year's wages for him. The telescope made him a local celebrity, as crowds of spectators jostled him from his perch above the photoshop for a glimpse of the planets. After they were gone, Barnard would resume his study of the sky, often until his eye froze to his eyepiece. In August of 1877, after a chat with Simon Newcomb, the respected astronomer who would go on to play a role in the Michelson-Morley experiment into the speed of light that would pave the way for Einstein, Barnard decided to focus his efforts on finding comets, a task at which he proved shockingly adept, discovering 15 over the next decade. To aid his search, he began a correspondence with Lewis Swift, a noted comet hunter and co-discoverer of the now legendary comet Swift-Tuttle. Swift encouraged H. Warner, a local patent medicine entrepreneur, to establish the Warner Prize, $200 to anyone in the US and Canada who discovered a comet in the concurrent year. Barnard would go on to win the prize 5 times. In 1882, impressed with his description of the recent transit of Venus, Olin Landreth, chair of engineering at Vanderbilt University, offered Barnard the vacant position at the university's telescope, the only one better than his own, within 200 miles. For the first time in his life, Barnard was a professional astronomer. As his career progressed, his eyesight became legendary. In one instance, he managed to spot a stellar companion to the star Beta Capricorni that had his fellow astronomers straining the best scopes of his day to breaking point in their attempts to confirm it. From the Vanderbilt, in 1887 he traveled to California to work at the then newly built Lick Observatory, home to what was then the largest refracting telescope in the world, where he employed his skill with photography to conduct extensive photographic surveys of the Milky Way, and attempted to solve the puzzle of dark nebulae. In 1892, Barnard made what was at the time his immortalizing discovery: a fifth moon of Jupiter, hailed worldwide as the greatest astronomical find of the 19th century. This seems strange now, that the first of the dozens of broken rocks orbiting the giant planet should be considered a more profound astronomical discovery than, say, Ceres, or Parallax, or Helium, or, well, Neptune. But you must remember that the moons of Jupiter were the discovery that launched modern astronomy, and no one had seen beyond Galileo's 4 since his eye first discerned them in 1610. Amalthea, as it was eventually called, was also the last satellite discovered by eye. All subsequent discoveries of satellites were made with cameras. This should give you some idea of just how profoundly gifted an astronomer Edward Barnard was. The same day he discovered his moon, a team of mountaineers had just summited a nameless peak of Mount Whitney, which they christened Mount Barnard, a name it still has today. Barnard would not get a star to his name for another 20 years, after he had defected to the even larger telescope built at the Yikes Observatory at the University of Chicago, which would become his final home. In 1916, while plotting the fine structure of the Milky Way, Barnard puzzled over a series of stars that appeared in images taken over a few years. Each appeared in a different position, but did not appear in the previous image. And then Barnard realized what he was seeing. Not several stars, but a single star racing across the sky in seeming record time. That stars had independent motion, or proper motion, had been known for hundreds of years. As they wend their way around the galaxy, their position relative to our own sun changes, gradually distorting the constellations. But none had ever been seen to clip through the spiral arms with the sheer vigor of this odd ingenue, whose record remains unbroken even now. Stars' respective speeds around the galaxy change little across the width of the galactic disk, a fact at considerable odds with calculations, which had suggested that, like planetary rings or any other construct of gravity, the galaxy's rotation should slow farther from the center. The reason for this anomaly is still not known, and led to the proposal of dark matter. Since star speeds are fairly constant, to display such a rapid proper motion, Barnard's runaway star, as it was initially called, had to be close. And indeed it is. In fact, at just 6 light-years distant, Barnard's star is the closest star to our Sun after the triple Alpha Centauri system. But wait, you might say, if Alpha Centauri is closer, shouldn't it have a higher proper motion? Well, proper motion is affected by more than just distance. Alpha Centauri is moving towards us, and so, much like a ball heading toward our head, we don't notice its sideways velocity as much. Barnard Star is moving towards us as well. In fact, in around 11,000 years, it will supplant Alpha Centauri as the closest star to our Sun, coming within 3.7 light-years, closer than Centauri is now. And there is a simpler reason for Barnard's high proper motion. It actually is moving peculiarly fast. It is currently traveling through the galaxy 110 kilometers per second faster than our own Sun, which has led astronomers to believe that it is not a born citizen of our stately galactic disk, but may in fact be a halo star. The galactic halo is a thin, spheroidal shell of stars enveloping the Milky Way, composed of the regurgitated remnants of smaller galaxies that ours has devoured in its 12 billion year lifetime. Its scattered stars tend to be old, with very low metallicities. Metal is astronomical shorthand for any element heavier than hydrogen or helium. So an astronomer might describe a star with high levels of carbon or nitrogen as rich in metals, even if neither are metals as we understand the term. In 1944, astronomer Walter Baade realized that stars were divided into two distinct populations, which he creatively dubbed Population 1 and Population 2. Population 1 stars, like our own Sun, had higher metallicities and were relatively young. Population 2 stars had lower metallicities and tended to be either very long-lived stars like red dwarfs, or near the ends of their lives. These two populations, Baade realized, unlocked the broad sweep of the universe's history. In the beginning, the universe was essentially an undifferentiated cloud of hydrogen and helium, with traces of lithium. This cloud collapsed into the first stars, which fused hydrogen and helium into heavier elements, i.e. metals, in their cores. The death throes of these primordial stars then blasted these metals into the universe, and fed the formation of the second generation of stars, now called Population 2. As the universe aged, the Population 2 stars themselves began to die, and seeded the galaxy with yet more metals, which then seeded the birth clouds of the next generation of stars, Population 1. Barnard is a Population 2 star. Its metallicity is roughly a quarter that of the Sun, and possibly as low as 10%. Evidence also suggests that it has a very slow rotation period. Our Sun rotates once every 25 days, but as each supercharged photon leaves the Sun's surface, it carries an infinitesimal fraction of the Sun's momentum with it, gradually slowing that rotation down. Barnard's rotation period is estimated at 130 days. These facts together point to one conclusion: that Barnard Star is ancient. Estimates for its age run as high as 12 billion years, nearly 3 times as old as the Sun, and as old as the Milky Way itself. Barnard Star has outlasted entire galaxies because it is a red dwarf, a tiny, dim, sputtering flame burning too slow to burn itself out. This is also why it took modern telescopes and the keen eye of Edward Barnard just to be noticed, despite being one of the closest objects to our Sun in the galaxy. For all that, though, despite being far, far dimmer than the Sun, it is still 10 times brighter and 30% larger than its better-known cousin, Proxima Centauri. Red dwarfs are known to flare, but Barnard appears to have quietened in its old age, flaring only sparely, possibly due to its slow rotation period. However, in 1998, a great flare was observed on the surface of Barnard Star, showing that, while it may be calmer than younger, feistier red dwarfs like Proxima, it still harbors a flicker of its old-timey rage. In the 1960s, if you'd asked someone versed in astronomy for a unique fact about Barnard Star, he, or less likely given the time, she, would almost certainly have told you that it was the only star other than the Sun known to have planets orbiting it. Yes, Barnard Star had a planet before it had a planet. The reason for this widely held assertion was an accomplished, charismatic astronomer named Peter van de Camp. Born Piet van de Camp in the Netherlands in 1901, van de Camp like many astronomers, came from a musical background and learned to play the piano at a young age. In 1940, he was appointed Associate Professor of Astronomy at Swarthmore College in Pennsylvania and Director of the Sproul Observatory, a position he would hold until he retired in 1972. He was universally praised as great company, a fascinating lecturer, and endlessly personable. His abilities with the piano were a large component of his charm, as he would keep staff parties going to the early hours of the morning. Unfortunately, his charm was also his greatest flaw, as it discouraged others from objectively checking his work, and allowed his discoveries to stand on his word alone. To be clear, Van de Kamp was not Percival Lowell, an ill-educated carnival barker with a flair for the dramatic. He was a highly credited, award-winning astronomer who happened to become unstuck on one particular issue. Van de Kamp was an astrometer, an astronomer specializing in measuring the distances and motions of stars. In 1938, he concluded that telescopes were powerful enough for astrometry to detect planets orbiting around other stars. Not directly, of course. As planets orbit stars, Newton's laws dictate that, in response, stars must move as well, much like a hammer thrower moves in response to the spinning of the hammer. Obviously, the larger the planet in proportion to its star, and the more distant its orbit, the more obvious the response would be, and the more easily its wobble could be observed in the star's motion across the sky. Friedrich Wilhelm Bessel, the discoverer of the first stellar parallax, had used just this method to find Sirius B, the white dwarf in orbit around Sirius, though of course white dwarfs are vastly more massive than even the largest planets. While the astrometric method bears some resemblance to the radial velocity method used to find the first extrasolar planet around a sun-like star in 1995, the two are very different, since the latter requires a spectroscope, whereas this method involved plotting the star's motion by eye, or rather by camera. Van de Kamp drew up a list of stars best suited to astrometric planet hunting, and top of that list was Barnard Star. Barnard Star had three advantages. First and most obvious, it was close. Ergo, any motions it displayed would be easier to see. Second, it was small, and so any planet's orbits would produce more noticeable wobbles. And finally, it was alone, so, unlike the gravitational house party that is Alpha Centauri, any observed perturbations would be due to planets and not to orbiting stars. In 1944, after 6 years of observation, Van de Kamp announced to the American Philosophical Society that he had identified a companion to Barnard Star of roughly 60 Jupiter masses, though even he admitted that such an object would strain the concept of planet. Today, we'd call it a brown dwarf. In 1963, after taking 2,400 images of Barnard Star, he stated that its companion's size was in fact 1.6 Jupiter masses, a planet by anyone's reckoning, and that it orbited its star in 24 years. There was a problem, however. Van de Kamp's planet did not behave like a planet, or at least any we then knew about. Its orbit was wildly eccentric, taking it from 1.8 AU. In our solar system, that would be between the orbits of Mars and the asteroid belt, and 7.1 AU, between Jupiter and Saturn. Nowadays, such an eccentric orbit would be nothing remarkable. We found exoplanets with far more extreme orbits. But in these older times, such behavior was unbecoming of a planet, and in 1969, Van de Kamp calculated a means to spare his planet's blushes. It was, in fact, not one planet, but two, one with a 12-year orbit and one with a 20-year orbit. Van de Kamp capped his moment with a popular article in Sky and Telescope, which introduced his planet to the wider public and essentially fixed it in the popular consciousness. But shadows were gathering. To date, no one else had seen any evidence of Van de Kamp's planets. The perturbations he was observing were 100 times smaller than Barnard Star itself. They could very easily be due to observational error. Even among those who accepted their existence, debate raged about exactly how many there were, from as few as 2 to as many as 5. In the early 70s, a shy astronomer named Nicholas Wagman attempted to replicate Van de Kamp's results and found nothing, though, perhaps for fear of upsetting Van de Kamp, he never published his findings. And then, in 1971, a graduate student named George Gatewood, newly settled at the Allegheny Observatory in Pittsburgh, began the study that would pave the way for the disexistence of Van de Kamp's planets. Gatewood had no desire to do this. He considered it mere follow-up work on Van de Kamp's discovery, and, like many people, didn't want to upset him should he prove him wrong. Years earlier, while still a young student, he had met Van de Kamp and gushed like a fan seeking an autograph, saying how amazing it was that he had found the first ever extrasolar planets. But his professors, perhaps growing wary of Van de Kamp's claims, pressured him into it, and so Gatewood made the planets of Barnard Star the topic of his PhD thesis. He too, however, soon grew uncertain. A fellow student noted that you could divide the orbits of Van de Kamp's planets by exactly 8.3 years, which seemed a remarkable coincidence. In 1973, a year after Van de Kamp retired, Gatewood published his conclusion. He found no trace of the planets observed in Van de Kamp's study. 4 months earlier, an astronomer named John Hershey attempted to follow Van de Kamp into the history books, and instead inadvertently revealed the source of his mistake. He used the Allegheny Observatory's Sproul telescope, the same telescope that Van de Kamp had used to track Barnard Star for decades, and turned to another nearby star, Gliese 793, hoping to replicate Van de Kamp's achievement. That he did, though perhaps not in the way he intended. Looking back in the historical archives, he found that Gliese 793 displayed the same perturbations that had bedeviled Barnard Star. Exactly the same. To the very year. Once in 1949, and once in 1957, both Barnard Star and Gliese 793 deviated from their paths exactly as described by Van de Kamp, the times corresponding, not coincidentally, with when the Sproul telescope had had its lenses replaced. Poor Van de Kamp had turned a pair of faulty refits into planets. What began as one of the greatest astronomical discoveries of all time ended as an abject lesson in one of the hardest truths of science. It's not a result until someone else confirms it. Van de Kamp never abandoned faith in his planets, and even into the 1980s continued to publish papers asserting their existence. But by then the community had moved on. With the exception, that is, of a team at both Keck Observatory and, appropriately, Barnard's old haunt at the Lick, headed by Joanne Choi, and including future planet finder Geoffrey Marcy. From 1987 until 2012, the team observed Barnard Star using the radial velocity method that would prove so useful finding the first exoplanet around a sun-like star in 1995. Their paper was notably careful to mention their instrument refits. While their study failed to find any planets, it did manage to establish a series of upper limits to what kinds of planets could exist around Barnard Star. They concluded that any planets above 2 Earth masses in size, with periods below 10 days, would have been detected, and thus that there were no planets larger than Earth in Barnard Star's habitable zone. They also concluded that the star hosted no planets with orbital periods of up to 2 years and masses above 10 times Earth's. This was seen by many as a tragic coda to Van de Kamp's sad obsession. Frankly, I can't understand why. The study didn't rule out planets around Barnard Star. It didn't even rule out an Earth-sized planet in Barnard's habitable zone. No, there are almost certainly no gas giants around Barnard Star, but that was always likely to be the case for low metallicity stars, and certainly no barrier to the formation of the Earth-sized planets we, as a species, are far more interested in. This year, this fact was highlighted when a paper appeared in Nature, published by Ignacy Ribas and colleagues, revealing the near-certain existence, 99% certainty, according to its proponents, of a large planet in orbit around Barnard Star. The study combined archival data with 2 years of new observations from both the Calar Alto Observatory in Spain and La Silla Observatory in Chile, for a total of 771 spectrographs over a 20-year span. Using a series of experimental cross-checks and statistical combing, they unearthed a consistent radial velocity shift lasting 233 days. This shift was inconsistent with Barnard's rotation period, which is estimated at 130 to 150 days. They concluded that the most likely cause is a planet with a mass roughly 3.2 times that of Earth, orbiting Barnard Star with a period of 233 days, comparable to that of Venus. However, due to Barnard's weaker gravity, to produce an orbital period of this length, the planet must orbit the star at a distance of 0.4 AU, comparable to that of Mercury. Somewhat ironically, the paper argues that given Barnard Star's closeness to the Sun and the relatively wide separation between it and its planet, the planet may be detectable using Van de Kamp's long-ignored method of astrometry. The Gaia spacecraft, the most comprehensive astrometric surveyor in human history, might be able to detect a Van de Kampian wobble in Barnard's motion through the galaxy. So what would this world, if it exists, be like? Barnard Star B, as the world is known, may be larger than Earth, with Venus's orbit and Mercury's distance, but to compare it to any of these worlds would be very, very wrong. Its orbital distance of 0.4 AU is still well beyond Barnard's habitable zone, at least any habitable zone as we define it. In fact, Barnard Star B lies beyond its star's snow line, the point at which water freezes and becomes part of a world's geology. But that does not doom it to an existence as a frigid, inert hulk. Its equilibrium temperature, or temperature if it lacked an atmosphere, is calculated to be at or less than 105 kelvins, an auspicious number, as it lies about as far above the triple point of methane as Earth's temperature does from the triple point of water. A substance's triple point is that at which it is capable of existing either as a solid, liquid, or gas. For water, the point lies just above 0 Celsius, and the fact that Earth's temperature cycles around this point is the reason why we call it the blue planet. Whether frozen as ice, falling as rain, raging in the ocean, or vapor in the sky, water's presence on Earth creates a geological kaleidoscope that shapes and reforms our planet on a daily basis, and of course, is the sole reason Earth is a living planet. Barnard Star B's temperature allows it to be another such world, though with methane rather than water. And thus, there is a world in our solar system you could compare it to. A world where just that balance exists, where methane rain falls on icy bedrock and washes down methane rivers into methane seas. But it isn't a planet. It's Saturn's moon, Titan. Saturn's distance from our blazing sun, at 9.5 AU, is comparable in effect to Barnard B's distance from its ancient flickering ember. And planetary scientists had assumed that Titan would possess boundless seas of methane comparable to our own. Unfortunately, when the Cassini mission finally unveiled the surface of Titan, it found that permanent bodies of liquid methane on Titan were apparently confined to its north polar region. Thing is, there's no reason for it to be. In fact, Titan's surface temperature, 94 K, is closer to the triple point of methane than Earth's is to the triple point of water. It should be a methane paradise. Even more puzzling, for the sheer amount of complex hydrocarbons present on Titan's surface to exist, models predict that an ocean's worth of ethane should be raining from the atmosphere. But that ocean is nowhere to be seen. Instead, the majority of Titan's surface is a rolling desert of hydrocarbon sand. There's only enough methane in Titan's atmosphere to support a hydrosphere for 200 million years, so unless Titan's atmosphere just popped into existence alongside the Stegosaurus, the additional methane and ethane must be somewhere. The leading candidate is underground, perhaps drained into crevasse-like fissures in the granite-hard water-ice crust. So Titan may simply be a victim of circumstance. Just because it happens to be a methane desert doesn't mean all methane worlds must be. In fact, Barnard B may be in a far more favorable position than Titan. At its distance from its star, unlike any world potentially in Barnard's habitable zone, it is free from tidelock and solar flares, and actually receives less UV than Titan does at its far larger distance from our Sun. This means that far less of the methane on Barnard's surface will have been photolyzed, leading both to more methane on the surface and also to a reduction in smog and potentially clearer skies. The stellar flux it receives is greater than that of Saturn, but still less than that of the moons of Jupiter, meaning that Barnard B is a world of darkness, never seeing a noon brighter than twilight. Some have argued that a world formed around a red dwarf like Barnard may have less methane than Titan. However, a world larger than Earth, like Barnard Star B, should have a highly active geology, which could allow it to produce its own methane through hot water interacting with rock, in a process called serpentinization. So perhaps we are being too egocentric when we say that Barnard Star B is outside its habitable zone. If it does indeed possess oceans of liquid methane, it may be as much a haven for life as our own world. I've already explored in detail the possibility of liquid methane-based life in my video on Titan, so I won't repeat myself here. But suffice to say, while speculative and arguably less likely than water-based life, it is at least conceivable. And don't forget one thing. Barnard B has seen its feeble parent star sputter across its twilight skies for 12 billion years. Monoliths of ice may loom over its shadowed surface that were as old as Earth when Earth was born. However improbable life may be on such a world, all probability needs is time, and Barnard Star has watched time itself grow old. If life has had a chance to find a foothold there, then we might have to face an unnerving truth about our place in the universe. Red dwarfs comprise 85% of all stars, and thus oceans of methane may far outnumber those of water. Whatever ancient creatures plod their way across their darkened shores may truly be the dominant form of life.